Hi there, Dr. Steve Kuchnicki again, and now I'm going to talk to you today about stress blocks, right? Stress blocks, as I hope you know, they're squares that we use that represent stresses at a point inside of a body, okay? So that means we need to have in mind what it is that we're looking at, the body that we're looking at. So that becomes very important in terms of the way it's loaded, because that'll help us determine, once we have the loading down, how the arrows, how the shear stresses especially, look on that body. And I often tell people, I have rarely, if ever, gotten angry at myself for drawing one picture too many. It's one picture too few that normally throws me off. So what I'm going to do is draw an extra picture about our stress block, right? So what we're going to have here is we're going to have some kind of body, right, with some kind of forces on it. I'll draw it as a simply supported beam, but it could be just about anything. All right, so we have a body. We've got some kind of load here. We've got some kind of load there. We've got some kind of load here, some kind of load here to make life more interesting. The actual values don't mean much, right? And we're interested in knowing what's going on, say, in here on this little stress block. The first thing to keep in mind, after I do what I always tell my students to do, and that is draw in your coordinate system. It's that important, yes, right? When we go looking for stresses, we need to be looking at internal forces. If we're looking at internal forces, we must be thinking in terms of a cut. Yes, a lot of times we'll draw a shear and moment diagram for this, but we have some kind of cut going through this, right? And what's going to happen if I look at that cut portion, right? I could draw a secondary FBD, or an FBD of the cut part. And again, what I'd find to be consistent with what I had above, but I'll use the same coordinate system so I won't redraw it. I've got a force going down, the applied load P1. I've got the reaction F1 going up. The way that I've drawn this up, it looks like that's the reaction. I still have my cut face. And in general, what I can have here is I can have a normal force, which we assume is positive outward. I could have a shear force, which we assume is positive downward, because that's the direction that spins the beam clockwise, right? That's our positive shear force. And a positive bending moment, of course, makes the smiling beam and bends the center line up. If we have all of these forces in those directions, then we use our familiar equations with pluses and minuses on the shear force, the moment, the normal force, and we get the right stresses back. So now what we have to think of, if we're thinking in terms of what's happening here for the purpose of a stress block, is first we have to always keep in mind that this is the cut face. Why is that important? Well, now, if I call this point A, just so it has a name, if I go to draw a stress block of point A, right, I'll go and note that I'm drawing a stress block. Well, here's my point A. I'll put A in the corner here. And why am I putting A in the corner? Well, that's because I want to put my coordinates on here. And going all the way back to my first free body diagram, my x-axis was to the right, my y-axis is up. This is on the side of the body. So I've got myself a y-axis going up and an x-axis to the right. Okay. Now, something else I tell my students all the time is that each of these loads gets to cause exactly one and only one stress, right? So what's going to happen is that the normal force N, right, this is going to cause a normal stress, go figure. It's going to cause sigma x equal to N over A. Why is it in the x direction? Because I've got a force in the x direction acting on a plane perpendicular to whose perpendicular, should say, is the x-axis, or a plane perpendicular to the x-axis. Take your pick. That's an x stress. V is going to cause a shear stress. We'll call it tau xy. Why is it tau xy? Because it's going to be a y-facing force. The shear force V is definitely in the y direction, and it's on that same plane whose perpendicular is x. So I'm going to have tau xy, and that's going to be VQ over IT. The moment is going to cause an axial stress, sigma equals minus moment y over I. And that sigma, well, that's going to be in the long direction of the body, because if I bend this thing, right, if I bend this thing, bend my stylus here, it's going to get longer and shorter from left to right, isn't it? Right? So that means if I put that in front of my bar, it'll get longer and shorter from left to right. That's the x direction. The strain's in the x, the stress has to follow. Hooke's law is a thing, right? So sigma x here. So that means my total x stress on my stress block, this is the part that people don't have trouble with, this is going to be equal, sigma x equals n over a minus my over I. No problem, no worries, no issues. And there's certainly going to be a shear stress that's going to be equal to VQ over IT, but which way does it go? And again, what we have to do is think in terms of the cut face. The other two blocks that I've drawn, right? First block, the cut face is on the right edge of the block. Second cut, the cut face is on the right edge of the stress block. Well, that means my cut face is still sitting here. And that tells me all I need to know about what the stress is going to do, what the stress block looks like. It tells me everything. Because that shear force V, if it's in that direction, if it's positive in this case, it's going to cause a force that goes downward on that right-hand cut face. Then, in order to have equilibrium, because again, this stress block is a piece of the overall body, therefore, I need to think in terms of this thing being in equilibrium, a part of a body in equilibrium. Any part of a body in equilibrium has got to be in equilibrium itself. So I need an equal and opposite force, and it's going to be over here on the left face. Well, now if I leave this alone, I mean, it looks like it's in force equilibrium, and sure, it's not going to slide anywhere, but that thing's going to spin. In order to stop it from spinning, I need to provide what's an equal and opposite couple. These two forces make a couple. I need to make another one that fights that. And that's why you get the 4 arrows. And this, of course, is just VQ over IT. And that's how we draw the stress block at A. Pretty straightforward, right? Let's throw a little monkey wrench into the works. Let's make another box up on the top and call it B. Part of the reason why I want to do this is because if you're thinking about this, and gosh knows I hope you are, you're looking at me saying, hey, why do you even bother with my over I? Isn't point A on the neutral axis if it's in the center? Yeah, it is. You're right, it is. I give up. You got me. We'll go to point B instead. And we could also choose any point in between, but there's a reason I want to choose point B. Right? Notice how point B shows up as a line. Okay? So B, we'll say it's on top of the body. Okay? So B is on top of the body. So that means if I wanted to draw a figure so I could actually see the block at B, what I'd have to do is I'd have to draw something like this. Okay? I can't see my forces. I'm looking down on the body from the top. That's what I'm doing. I'm looking right down at this thing. Right? That means the y-axis would be coming out and poking me in the eyeballs. It'd be poking me right in the nose. Just like my stylus just did, right? The y-axis coming out of the page at me. The x-axis is going this way, to the right, and then the z-axis must be going down. Point B, then, must be sitting up on top like this, where again, that's my cut. So now if I was to draw that stress block, I used blue before, I'll use blue again, right? My stress block then for point B has an x-axis to the right, a z-axis going down, and now I have to think about what those three loads do, and they don't appear very well in this figure, honestly, right? I could certainly have loads in the xz direction, but notice how none of my forces are really appearing, so I'm going to go back up for a sec. We're going to go pick up those loads. I've got to think about N, M, and V. Well, they get to cause the same stresses, right? So N is still going to cause sigma x equals N over A, and M is going to cause sigma x equals minus my over I. That's not going to change. They don't cause different stresses just because they're at different points. They cause the same thing, right? So certainly, I'm still going to have an axial stress in the x direction equal to N over A minus my over I. That shear stress, though, right? That shear force was in the y direction. The shear force is coming out of the page at me. Shear out of page. Shear out of page. Doesn't sound like shear to me. And that's because, again, it's a y-directed force on an x-directed plane, right? So what this is telling us is that the force V does not cause a stress here. There's two reasons for that. There's two ways to look at it, really. The way I just kind of mentioned, I'll call number one V sub y, because later on we can have V sub z, a shear force in the z direction. So I'm going to call this Vy, just so we know what it is. It's not in the xz plane, right? When I had point A, I had an xy plane. Hey, a shear force in the y direction can cause a shear stress in the xy plane just fine. Z direction, not so much, right? Can't really do that. The other thing is that Q equals 0 in VQ over IT. I'm on top of the area, right? So if I was to go all the way back, and I will, right? You go all the way back here, point B is on top of the area. Well, how much area is there above point B? I don't see any. And since Q is equal to the centroid times the area, well, 0 area means 0 Q, means 0 shear stress at that point. Aha. The other way, the mathematical way for us to see that, right? And I'll note that's because there's 0 area above the cut, or above B, shall we say. Right? Since there's no area above point B, we don't have any Q. We don't have any Q for VQ over IT. We have no shear stress due to the force V. It's going to try, it's going to fail, right? And we just have this situation instead, just the normal stress. Big takeaways here, of course, are 1, the plane changes. Point B is an XZ plane, point A is an XY. 2, the stresses can change. What each load causes does not. The total stress can change because point B is going to have the largest bending stress. I agree with that. It's on the top edge, right? But point A is going to have 0 bending stress. They use the same equation, though. Still my over I at both points. And, of course, again, that shear stress, right? The direction of it. We look at the cut face, and we see what the forces are doing on that cut face. And that tells us what directions our stresses take. Okay. As always, thanks a lot for watching.